Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on what you need to know for the chapter on limits. So what we're going to do is just cover some basic problems that we want to make sure you kind of mastered or remember or feel a little bit more comfortable with before we start getting into all the problems for identifying the limit. So what we're going to work on here is covering how to identify the asymptotes, horizontal, vertical, and oblique. Then we are going to jump into identifying the discontinuities, or identifying if a function is continuous or discontinuous. And if it is discontinuous, if it is discontinuous, then identifying the type of discontinuity as a hole, an asymptote, or a jump. So we have, again, some more rational functions here. And then we're going to also work into some piecewise functions. And then we'll also work into evaluating the function just for some given numbers, finding the value of the function for certain input values, and then working on sketching the graph of the following functions and then determining the domain. So again, just looking at some basic functions, really the square root, the absolute value, and the reciprocal function, but just kind of really understanding how the domain kind of works for each one of those kind of functions, as well as the transformations from their graph. All right, so let's go ahead and get started up here and just kind of do a quick little review of the asymptotes, how to identify them. And remember, when we're looking at this, when we're identifying the horizontal asymptotes, we're going to use the horizontal asymptote test. When we're looking for vertical asymptotes, we're looking for values that are going to make the denominator equal to 0 that do not get divided out, because if they get divided out, they're removable and therefore they're holes. And remember, oblique asymptotes occur when we do not have horizontal asymptotes, therefore we can use division. But again, you have to be careful for holes. So how do holes exist again? Well, the holes are going to prevent us from having an asymptote when they get divided out. So the first thing we always want to do is just look at the simplified form of our rational function. So in this case, you can see I can factor out an x. By factoring out an x, I'm left with an x minus 1 all over x. So you can see these x's divide out here, just leaving me with the equation x minus 1. I don't know why I divided out the x. So really what this equation is it is a line, x minus 1, with there is a hole. So we can say there is a hole at x minus 1. Okay? So this is very important because since there's a hole at x minus 1, there is no vertical asymptote. There is... So there's no vertical asymptote because now you can see that the equation is, oops, I'm sorry, I kind of wrote that wrong. All right, so my hole is going to be at x equals 0. So there's no horizontal asymptote, and there is not going to be a vertical asymptote or horizontal asymptote because using the horizontal asymptote test, the degree in the denominator is smaller than the degree in the numerator. So there's no horizontal asymptote. And a lot of people think, oh, since there's no horizontal asymptote, then there has to be an oblique asymptote or a slant asymptote. But again, in this case, there's no slant asymptote because, again, we have that hole. So I started with this problem that, we want to make sure we're very careful by identifying holes because holes are going to impact our asymptote equations for vertical, horizontal, as well as slant. So in this case, we literally just have a line, y equals x minus 1 with a hole at 0. All right. So let's get into another problem here. And again, we have a little bit more advanced factoring. We have a trinomial, which looks like I could factor that into a perfect square trinomial. I'm just going to expand it out, though, as x minus 1 times x minus 1. Over here, I can factor out a 2. That's going to give me a x squared plus 2. Now, again, in this case, you can see that that doesn't really help me as far as factoring that out. You can factor out the 2, but that doesn't give me a difference of 2 squares, which is something I would have been nice for. So now we can go ahead and look at our vertical asymptotes. So I always like to look at the vertical asymptotes first. Actually, let's just write that in the factor form. I always like to write this in the vertical asymptotes first because really since there's no holes here, nothing gets divided out from the denominator to the numerator, I can just set the denominator equal to 0. Now you can set the denominator after you factor something out, or you can set it in this form. But the important thing here is when you set this denominator equal to 0, you're going to subtract 4, divide by 2, then you're going to try to take the square root of a negative number. So therefore, that's going to be in your imaginary number system. And again, there's not going to be a asymptote. We're looking for a real number where the graph is going to be approaching. So therefore, in this case, the vertical asymptote, I'll just say 2x squared plus 4. I'm just going to set that equal to 0, but therefore, there's not going to be a vertical asymptote. Now, as far as the horizontal asymptote goes, I'm going to use the horizontal asymptote test. And remember, the horizontal asymptote test is when the degrees in the numerator is equal to the degree in the denominator, you're just going to take leading coefficient over leading coefficient. So therefore, that's going to be y equals 1 over 2. And since there is now a horizontal, I'm going to call this a slant. It's just a little bit easier. Now that we have a horizontal asymptote, we know that we have a slant asymptote is not going to exist. So again, we can see that a vertical asymptote does not exist when there is a hole, it gets divided out. We can also see a vertical asymptote does not exist when it's set equal to 0 is going to be for imaginary numbers. So just some food for thought, some things to remember. All right, next example, there's really nothing I can do in the numerator, but I can divide out or factor out the denominator. So that's going to give me an x minus 2 times a x minus 1. What two numbers multiply to give you 2, add to give you negative 3. All right, so again, since nothing gets divided out here, my vertical asymptote is just going to be basically setting my denominator equal to 0. Now in this case, I'm going to use the factored form. That's why that was kind of helpful in this case. So I can have a vertical asymptote at 2 and a vertical asymptote at 1. As far as my horizontal asymptote, the horizontal asymptote test states that when you have a degree in the denominator, which is larger than the degree in the numerator, you have a horizontal asymptote at y is equal to 0. So in this case, again, we have a horizontal asymptote, so I'm not going to have a slant asymptote or an oblique. All right, so next equation, or next function here, we can factor out the numerator. So if I factor out a 2, I get a x squared minus 4 all over an x plus 1. That can be factored a little bit further down to x minus 2 times x plus 2 all over x plus 1. But again, notice nothing gets divided out, right? So there's no holes that are going on in this case. So my vertical asymptote is going to be the values that make the denominator 0. So I'll just say x plus 1 equals 0. And I can say x equals negative 1. The horizontal asymptote, now the degree in my denominator is smaller than the degree in my numerator. So via the horizontal asymptote test, there is no horizontal asymptote. So that's just like this equation over here. The difference from this equation, this function to that function, is even though this function had the exact same thing, right? The degree is 1, degree is 2, degree is 1, degree is 2. This one also had a hole. But either way, whenever your degree in your denominator is smaller than degree in your numerator, you're not going to have a horizontal asymptote. And then we go and look at the slant asymptote. And to identify the slant asymptote, all we're simply going to do is apply long division. So we're just going to divide the divisor, into the dividend. So 2x squared minus 8. So remember, for long division, all you're going to do is take the first term and divide it into the first term of your divisor. So x divides into 2x squared. That's going to be 2x times. You can always check your division, because when you multiply 2x times x, you should get the exact same form, which is correct. And then I have a 2x plus 1, which is going to be a positive 2x. Now, a lot of people get confused in this portion because they can't subtract negative 8 minus 2x. But again, don't worry, then you don't subtract it. Like, it's really like 0 minus 2x. So therefore, it's going to be a negative 2x, and negative 8 minus 0 would be a negative 8. Now, the nice thing about identifying the slant asymptote is something that we learn later in this chapter. We don't really care about the remainder. We only care about the divisor. So all I need to do now is just say x divides into negative 2x. That's going to be a negative 2 times. Negative 2 times x is a negative 2x. Negative 2 times 1 is a negative 2. Again, we don't care about the remainder. I mean, I'll do it just anyways, just to kind of see the answer. But again, my answer is just going to be y equals 2x minus 2. So all we're going to do is take that, the quotient here, and just set it equal to y, and that's going to be your vertical or your slant asymptote. All right, next equation. Again, we'll factor it, see if we have some holes or whatever else may be going on. So here I have a quadratic where a is not equal to 1. So therefore, I'm still going to factor it the same technique. You know, I know it's going to give me a binomial times a binomial. Now I just want to be able to see, this doesn't look factorable, actually. So that's going to be 2x plus 3. 2x times 3, that'd be 1 and 2. No, it does. It is factorable. So that's going to be a plus 1, and this would be a plus 2. Let me see if that double worked. So that's a 2. No, that's supposed to be a 3. Idiot. There you go. Let's just double check my work. 2x times x is 2x squared. 2x times 1 is 2x. 3x, 3 times x is 3x. So 3x plus 2x is going to be 5x. And then 3 times 1 is 3. Okay, very good. Now my denominator, that's a little bit easier. That's going to be factored into an x plus 3 times an x plus 1. Okay, so now in this case, you can see this x plus 1 gets divided out. So 2x plus 3 over x plus 3. So the x plus 1s, these whole quantities get divided out. All right, but so we have a whole. So we're just going to say there's a whole at x equals -1. That is still a discontinuity. That still makes the denominator equal to 0, but it got divided out. So therefore, we're not going to include it as our asymptote because it's a whole. So now we go through our vertical asymptote. Again, we're just going to set my denominator equal to 0, but we're not going to include -1. So we're just going to set the x plus 3 equal to 0, and we're just going to get an x equals -3. And that's the very important part about this. These are the problems where students get tripped up, is because they immediately just set the numerator equal to 0 and solve. But again, we got to be careful for those holes. As far as the horizontal asymptotes go, we can just go back from our original equation here and see that since my degrees are exactly the same, I have a numerator over another numerator. So therefore, my horizontal asymptote is going to be y equals 2. And since we have a horizontal asymptote, therefore, we're not going to have a slant asymptote. All right, last equation here. Again, want to look into factoring here. So I factor out a 2, x minus 2. Here I'm going to factor out a 2 first. I get an x squared minus 3x minus 4. I can factor that further, but it doesn't look like it factors to anything down. So therefore, the 2 times a x minus 4 times an x plus 3, or x plus 1. Okay, now one of the common things that students like to do here is they like to divide out the 2's and say there's a hole at 2. No, there's not a hole at 2. Remember, holes and asymptotes occur for values that make the denominator equal to 0. So even though this can be simplified, right, into x minus 2 over x minus 4 times x plus 1, there is no hole that's going to occur as far as division, all right? As far as vertical asymptotes go, though, you don't really need that 4 or that 2. That is just an extra multiplier. So you can just set x minus 4 times x plus 1 equal to 0, and we get x equals 4 and x equals -1. As far as my horizontal asymptotes go, I notice the degree in my denominator is smaller than the degree in my numerator. So therefore, I'm going to have y equals 0. And again, in this case, my slant asymptote is going to be none. All right, so really that's just a good review. Remember, just the main important thing, especially for these slant asymptotes and vertical asymptotes, before you get so happy about adding them in there, make sure you always simplify your rational expression and look for those holes because those are going to affect it. And in the same respect for horizontal asymptotes, just make sure you understand that horizontal asymptote test. All right, so now let's go and talk a little bit more about the continuities. So remember, holes are going to be what we call our removable discontinuities. Asymptotes are going to be non-removable discontinuities, as well as jumps. For rational functions, we're not going to be dealing with jumps. We're only going to be dealing with holes and asymptotes. So therefore, we basically just want to factor something out. If it gets divided out, it's a hole. If it does not get divided out, then it's an asymptote. But remember, the factor is not the hole or the asymptote. It's the value that makes that factor equal to 0 is where those discontinuities occur. All right, so let's look at this first one here. So this one's going to be x minus 4 times x plus 1 all over x minus 4 times x minus 1. Okay, now again, these quantities, so what I did by factoring is I rewrote this now as a product. So now that it's written as a product, I can divide out terms that are exactly the same, right? So I have an x minus 4 over an x minus 4. They can now be divided out. but you can't just divide like the 1 and the -1 and just say I'm left with like x over x or something. So you can only apply the division property when you have your quantities separated by multiplication, which you can see these quantities inside the parentheses are separated by multiplication. So therefore, we're just going to be left with x plus 1 over x minus 1. But again, we want to be careful. We don't want to say the whole occurs at -4. The whole occurs when x minus 4 is equal to 0, because x minus 4 is what got removed. So that occurs at x equals 4. The vertical asymptote occurs when x minus 1 is equal to 0, which occurs at x is equal to 1. So you can see how those how they differ. A lot of students will make that mistake as far as they see the -1, they just set it there, but it's actually that factor equal to 0. All right, so again, a lot of students want to go ahead and divide. They say, oh, the 3 and the x squared, like they're multiplied. And, or, just divide out the 3's or divide out the x squareds or divide out the 3x squareds. But we can't do that in this problem because these, right now, they're not separated by multiplication by both terms, right? So you just can't divide that out and just be left with 1 over 6. However, in the denominator, we can factor out a 3. So by factoring out a 3, I'm left with a x squared plus 6, okay? And by factoring out an x squared plus 6, again, you can see that these 3's, do divide out. So you're left with an x squared over x squared plus 6. Again, we cannot divide out these x squareds. So this one actually does not have any asymptotes or any holes. This one is actually continuous because, again, when we're looking for a discontinuity, that is going to be a value that is, for a rational function, is going to make the denominator equal to 0. So when I set x squared plus 6 equal to 0, this is something I did in that second problem, I believe. You're going to get x squared equals -6. Well, when you try to take the square root now of both sides, you have plus or minus the square root of -6. Like, you can't take the square root of a negative number in the real number system. So therefore, this function is continuous. All right, so now let's go and look into piecewise functions. So for the piecewise functions, basically what we're going to want to do to be able to identify the discontinuity is kind of know what the graph looks like. And, we spent a whole bunch of time in functions graphing them. So we really want to make sure we kind of understand the parent graph. All of these are changing at 0. So in this case, we have the absolute value function. So what I'm going to do is I'm just going to draw like a rough sketch of each graph. And then just kind of go from there so we can kind of look at the graph and identify. Remember, a hole is basically just going to be an undefined value in the graph. An asymptote is going to be a value where the graph is actually approaching. And a jump is going to be a graph where it's kind of going from one function to the next. So in this first one, we have absolute value of x, which is going over from here to here, but it says x cannot equal 0. Well, on the absolute value function, 0 is 0, right? But then it says when x equals 0, we have 3. So 1, 2, 3. All right, now again, even though the function is defined at 0 at 3, there's still going to be a hole, right? There's still a discontinuity there. There's still an undefined value at x is equal to 0. So we're just going to say there is still a hole at x equals 0. And there's just going to be another value that also includes it based on the rule of the piecewise functions. For g of x, the next one. So we have x squared plus 1, which is x is greater than 0. So that's going to be plus 1 greater than 0. And then we have negative x squared plus 1. And then that's just going to be basically going a parabola going down. So again, you can see here, now in this case, we have a function that is, again, not defined, though, at this hole, right? So it's still going to be a hole at x equals 0. So again, even if it has a defined value or it does not have a defined value, there still is a hole. There's still that undefined value on the graph. For the next one, negative 2x plus 1. So again, remember the 1 is going to be kind of your y-intercept. And then we're going to go down to the right one. So probably going to look something like this. This says, oh crap, sorry. It's less than or equal to 0. So that means I'm actually going to go up to the left one, kind of go in that direction. And it's less than or equal to, so it's going to be an included circle. All right, so that looks something like this. And then my other equation is 1/2 x minus 1. So it's going to be down 1, and that's going to be greater than 0. So it's going to be an open circle like up 1 over 2. So that's going to be something like this. Now in this case, you can see that the graph is actually not connected at all, right? So at least with these, they had that undefined value, but that was it. You just had one value that was undefined. Even though this is defined later, there's still that undefined value portion of the graph. Whereas this graph, you literally have to go, you have to jump from one to the next. So therefore, this has a jump at x equals 0. And this next example here, you can have 3/2 x where x is greater than 0 and 1/4 x squared. So we have 3/2 x squared. So that's for their y-intercept is at 0. That's going to be an open circle. So 1, 2, 3 over 2. Something like that. And this other one is going to be 1/4 x squared, but in this case, x is less than or equal to. So that's going to be some like y parabola, but it's equal at 0. So even though this function is undefined, this function is defined at 0. And since when you plug in 0 for both of those functions, you would be at the point 0, 0, we can see that this function is continuous. All right, for the next one, it's really just finding the value. You're just gonna, when we say f of 1, f of 0, f of -1, we just want to find the value of the function. So all we're simply going to do here is just plug in the function and just simplify. So f of 1 is going to be negative x cubed minus 2. Why am I keep on doing that? Why am I writing the 1, x? No, we're going to replace x with 1. So 1 cubed minus 2 times 1 squared plus 1. All right, so just remember, whenever you have a positive number raised to an odd power, it's always going to be like a positive number always raised to positive, so that's going to be positive times a negative, so that's a -1. That's a positive times -2 plus 1. And therefore, this answer is going to be -2. For f of 0, this one's kind of nice because everything is just going to go to 0, so that's just 0. And then f of -1, this one gets tricky with students. You just got to be careful. Whenever you have a negative number raised to an odd power, it's going to be negative. Whenever you have a negative number raised to an even power, it's going to be positive. Okay, so that turns into a negative times a negative is a +1. That becomes a positive times a negative, so that's a -2, and then that's a -1. And 1 minus 1 is 0, so therefore that goes back to -2. So -1 minus 1. Interesting. All right, for the next one. Now we just have plug in f of 1. So again, we're just going to do f of 1 squared plus 1 minus 1. I always like to put parentheses though when I'm evaluating, so therefore I can remember what I am doing here. Now in this case, it's important to see that when you plug in 1, you're going to make the denominator equal to 0. So therefore I'm going to write undefined. For f of 0 here, the nice thing if you remember this is, you can simplify this. I'm just going to do it, but if you remember from our rational functions unit, when you have a rational function and you're plugging in 0 in for your variable, you're just going to have the constant over the constant, which is typically what we did for the y-intercept. So 1 minus 0 in this case, it's really just going to that goes to 0, that goes to 0, that goes to 0. So you're really left with -1 over 1, which is a -1. And last but not least here is we have f of -1. So therefore, that's going to be 2 times -1 squared plus -1 minus 1 all over 1 minus a -1. So again, this one becomes a positive, so that becomes a 2. This becomes a -1 minus 1, so that becomes a -2 over 1 minus a -1, which is 2. But 2 minus 2 is 0. 0 divided by 2 is 0. So you can see, again, there's a lot of times just being really tricky with those positive and negatives. All right, the next one, f of x equals square root of 2x squared minus 5 of x. So if I plug in f of 1 here, I get 2 times 1 squared minus 5 times 1. Let's see, that becomes 2 minus 5. So 2 minus 5 is going to be a -3. And again, we cannot take the square root of -3, so therefore that is going to be undefined. For f of 0, everything is just going to go to 0, right? So we have square root of 0, which is just 0. And then last but not least, we have f of -1, which a lot of people are like, oh, you can't take the square root of negative. Yeah, but when you plug in the negative, you actually don't have a negative radicand, right? So -1 squared is going to be +1 times 2, and that's plus 5, which equals the square root of 7. which you could just go ahead and simplify, to 2.64575513. But we'll just keep it as a square root of 7. All right, last but not least here is sketch a graph of the following functions and then determine the domain. So in this one, we have y equals 1/2 x plus 1. So we need to identify, okay, so the first thing we need to do actually for these two functions, we need to understand what is the domain of f of x equals the square root of x. And if you remember, the domain here is going to be from 0 to infinity. Let's just do the y then. Okay, for the equation y equals absolute value of x, the domain is all real numbers. And then for the function y equals 1 over x, so what I'm doing is I'm doing the parent functions for each of these. The domain is going to be from negative infinity to 0, union 0 to infinity. Also, just a nice fancy way of saying all real numbers except for 0. Okay, so I have y equals 1/2 square root of x plus 1. So we want to see what's happening with the graph. Well, again, we have this 1/2. So everything that's happening to this graph right now is outside of the function. That means it's going to impact it vertically. The nice thing about having impacts vertically is that makes no change to the domain. You can see here my domain is still going to be from 0 to infinity because the only thing that's happening is the graph is being vertically compressed by 1/2 and then shifted up 1. So we need to know what each of these graphs look like. Because if we don't know what these graphs look like, then we're not going to be able to do any graphing problems. So remember, this is the square root from all positive numbers. This is the V-shaped graph, and this is that hyperbola graph. Okay, so all I'm going to do is I'm going to be compressing this graph and shifting it up 1. So again, I'm just trying to make something look, just a rough sketch here. And then we can say the domain, though, is still going to be from 0 to infinity. All right, for the next one, we notice that I'm multiplying by negative on the outside. That means it's going to be a reflection, but it's going to be a vertical reflection. So vertical reflections are reflections about the x-axis. And then I'm subtracting a 1 inside the function. So again, now that's inside, that's going to be a horizontal shift right or left, which is going to be a shift 1 unit to the right. Now, again, the nice thing about the absolute value functions is the domain is all real numbers. So it doesn't really matter what we do to the graph. The range obviously changes here, but the graph is going to be shifted 1 unit to the right, not to the left. I have no idea how that happened. So make sure you understand that from our transformations. Remember, it's always the opposite on the inside. So the range changes from negative infinity to 0, but as far as the domain goes, that does not change. Negative infinity to infinity. There's no discontinuities for the absolute value function. All right, for this function though, we do have some discontinuities if we were to change horizontally. But the nice thing about this is we're actually not changing horizontally. So in this case, reciprocal function is odd, if you recall. So there's a lot of different ways we could go ahead and write this. We could write it as like 1/2 x. So you could describe this as, again, another vertical compression as well as a reflection about the x-axis. You can see this is actually happening twice. Or another way you could look at this is you could say it's a reflection about the x-axis and going to be a vertical stretch or horizontal stretch, I'm sorry. So again, we could also look at it like this. So the nice thing is, since this is an odd function, it doesn't really matter which way you want to look at it or how you want to describe those transformations. The graph is going to have that same thing. It's going to be kind of a compression, so I don't really focus too much on the compression or the stretches. But again, the nice thing is we reflected it and we stretched and compressed it. We have remember the reciprocal function has a vertical asymptote at x equals 0. So the graph is undefined at x equals 0. But by reflecting and stretching and compressing, the graph didn't do anything. So my domain is still going to be negative infinity to 0, union 0 to infinity. All right, last round of examples. So this one is 2 minus x. We need to make sure when we're doing these problems that we put it into our transformation form. So that's going to be negative x plus 2, which is a negative times x minus 2. Now we can see that is a reflection about the y-axis and shifting the graph 2 units to the right. So now I have my graph being shifted 2 units to the right and reflected about the y-axis. So now you can see my domain has completely changed. Now my domain is from negative infinity to positive 2. So again, it's very important to make sure that you rewrite it into your B and C form. Same thing here. Now, again, we're not worried at this point as far as being the domain, right? We already know the domain is all real numbers. That's never going to change for the absolute value function. However, we want to make sure we write this with our correct transformations. A lot of people will say it's 4 units to the left, but no, you have to factor out that 2. When you factor out the 2, you get 2 times x plus 2. So actually, this graph is being horizontally compressed by a factor of 2, as well as being shifted 2 units to the left. So the graph would look something like that. Yeah, so again, the domain, though, is still going to be negative infinity to infinity. All right, for the last equation, we have y equals 1 over x plus 1 minus 2. So again, we can see we're adding 1 inside the function, so that's going to shift it to the left. So if the graph is shifting to the left, if we have a vertical asymptote at x equals 0, and we shift the graph 1 unit to the left, that means that the asymptote is going to shift 1 unit to the left. I didn't talk about this because we were composed of a domain, but if you remember from the reciprocal function, we have a horizontal asymptote at y equals 0. So if the graph gets shifted down 2, that means my horizontal asymptote just got shifted down 2. There's no other reflections or stretches or compressions. So just by following these operations, I'm shifting 1 unit to the left and 2 units down. So now basically I just need to do my, little hyperbola here, just doing a rough sketch. And you can see that's where the graph is going to look. Again, I asked to find the domain. Well, again, the original domain was negative, all real numbers except for 0. Now the graph got moved 1 unit to the left, so it's going to be all real numbers except for -1. And there you go, ladies and gentlemen. That is it for the limits. Obviously, we are going to be covering a lot more different types of problems for limits, but I feel like if you have a good, solid foundation for transformations, basic functions, their graphs, how to evaluate functions, understanding, again, discontinuities with piecewise functions, with rational functions, as well as understanding the asymptotes, you're going to have a good foundations as we get into limits. So I will see you on that chapter, and I look forward to helping you out on the next video. Cheers.